recording on the clock. Okay, let's get started. 7 o'clock. So, guys, this is a specialty class. Yesterday, I know we talked about controls a little bit. Today, we're going to talk about capacity controls. So, capacity controls being like unloaders, variable speed, two-stage, Carlisle compounds, that kind of stuff. So, if none of that made any sense to you, then welcome to the class, and we'll run through this. I'll give you guys opportunities to answer any questions once we cover a subject. I did take this slide deck from somewhere else, so there's a couple things that I'm going to throw in there just because I went through it last night, and there's some things I want to make sure we cover as well. So what's the importance of capacity controls, guys, is it's two things, and we'll just go through that. It's the compression ratio. And so what the compression ratio really is the absolute pressure on the suction line to the absolute pressure on the discharge line at the compressor. So for instance, you take your head pressure, pounds per square inch absolute, divided by the suction pressure. So, and that is what your compression ratio is. What that's telling us in a more granular detail type thing is how much volume of cool gas per stroke that compressor is getting. So because if you have a really high head and you have a really low suction, so on that downstroke, there's always a little bit of discharge pressure in that cylinder. So and on that downstroke, if it's really high, it has to fill up, it has to drop pressure in order for that reed valve on the suction line to open. And so it's less new gas volume introduced per downstroke. And so what that does over time is that refrigerant is still absorbing heat inside of that compressor. So it's absorbing heat through the body of the compressor, and then it's absorbing heat in that heat of compression. So if you have less new gas in there, you have less heat absorption. So over time, as that's pumping, that piston's going up and down, it's not absorbing enough heat, and so it begins to overheat the compressor. And that's really what it comes down to, and that's why compression ratio is so important. It's really telling us that, you know, we have a good measurement of new cool gas being introduced to that each cylinder stroke. So low load causes low suction pressure. So meaning if there's, for whatever reason, if the doors are shut at night, or, you know, it's a cooler time of year, for whatever, we don't need as much heat absorption happening at the evaporator, then we don't pick up as much heat there, so it drops that suction pressure down. So as that suction pressure, or our optimal running suction pressure is low, really low. Like if we're running a freezer case or a POS freezer, we're going to run that fairly cold anyway. And so that's going to, in essence, because it's temperature pressure related, we're going to have a very low suction pressure. So any of you guys that are rack technicians, you know what I'm talking about. If you've dealt with R22 racks, what do you always see with R22 because it runs such a high compression ratio? We see liquid injection and head fans and oil coolers on those. Those are all cooling mechanisms to help cool the refrigerant and oil in the system because of such high compression ratio. That's why. Okay. So high compression ratios cause heat. Obviously, what I told you, they don't cause heat. They just don't absorb as much. Remember that refrigerant in vapor state, as it leaves the metering device and you get your pressure drop across your TXV, it starts its absorption. So it continues to absorb heat as it goes through the evaporator. That's what our superheat measurement is at the evaporator. We're seeing how much heat absorption is happening at the evaporator, okay? And then as it gets to the compressor, we're measuring it there as well because it's still happening. It happens all the way until it hits the condenser. That first bend of that condenser is when it starts to de-superheat, and then it starts to subcool. The difference is what state the refrigerant's in. Okay, so if you guys have ever ran your fingers down a condenser coil and you get 2/3, 1/3, you know what I'm saying there? It feels 2/3 hot, 1/3, you know, cooler. That's where it's changing phase. So it's going from a high pressure vapor to a high pressure liquid. So, and that's where, depending on the state of the refrigerant, is where it's either de-superheating or it's subcooling. Okay, we can talk more to that when we talk more about superheat, when we go more into superheat and subcooling on the beginning and advanced classes. Heat causes compressors to fail. two biggest failures of compressors is excessive heat and voltage issues. So that's what we deal with in this. So they always, any manufacturer will tell you what keeps compressors alive: cool gas. Okay. To protect compressors from low load, use capacity control. So as you guys are getting into, what I wanted to put in here and plug in here is like, not only do we use capacity controls for compression ratios, but we also use them. Obviously, if we can narrow up that compression ratio, there's going to be significant energy savings. So, and we're going to lessen our cycle time. So that life of that compressor is going to increase the less times we cycle it on and off. That's why short cycling is bad, because it overheats, number one, and because it's hard on the compressor. So that start-stop. So does anybody know how often we should cycle? From Copeland spec, I read this out of the book. Does anybody know where Copeland shoots for in an hour, how many times a compressor should cycle? We've talked about it in past classes. Anybody remember?
No more than 6.
Correct. So they're shooting for 6, no more than 6 times a cycle. So, and that's on-off start. So capacity controls, what they allow us to do is continue to sorry, one second. Hey, can you mute your phone? Whoever's at Costco. They use these capacity controls to keep that compressor running, but then just to unload it or, you know, ramp it down depending on the capacity control they're using. So it's capacity control usually is used to match. So they'll engineer it for the load that it's controlling, whether it be, you know, on a rack system. They're going to look at the overall BTUs that rack could use. They'll usually use stage 1 or stage 2, or possibly a satellite compressor to unload. So on single systems, they'll use it based on maximum load, and if they have multiple equipment tied to it, or if it's like an AC unit and they know it's going to have different times a year, it's going to instigate different loads depending on the application, they'll use capacity controls. So if the load drops, reduces the compressor efficiency. So it's less, the higher your compression ratio becomes, the less efficient. Remember, if we're trying to pump vapor through that compressor, the tighter we run that compression ratio, the more vapor per stroke we get, which means we're running efficiently. So a lot of people have tried doing this different ways. So we'll get into that as well. One method is to reduce the compressor pumping. So block suction ports so vapor cannot enter the cylinder. This is called unloading. So example, I'll show you some slides. As each heat status satisfied, the solenoid closes. Suction pressure starts dropping. Low pressure switches activates the unloaders. Unloading prevents suction pressure from going too low. So this would be, doesn't have to be necessarily, but just for show, so you guys can kind of get the gist of it. We have 310. Hold on a second, I'm trying to get my graphics going here. So right now you've got all 3 walk-ins running. All cylinders are loaded. So everything's loaded. The compressor's at full capacity. So one walk-in satisfies. So on mechanical unloading, they're going to use a low pressure switch. As the pressure drops on the compressor, it's going to unload one of the heads. Okay, if it's got 2 unloaders, you'll have 2 low pressure controls. One will be set at a higher pressure, one will be set at a lower pressure. So as the pressure drops, remember, as the pressure drops, the compressor will load one head or the other, or both heads at the same time. And then as the pressure rises, as load comes back and pressure rises, it'll load the compressor back up. So compressor drops to 20 horsepower. So this is a 30 horsepower compressor. They're saying that you need 10 horsepower for each walk-in. So then 2 walk-ins satisfy, 2 systems pump down. Now we're running, you know, a very large compressor on, we're running a third of what we need. So therefore, a second low pressure switch energizes on the other unloader, the cylinder unloads. So if this is a W body compressor, you've got 3 heads. So now you're really only pumping through 1 head of all 3. You get it? So you keep that capacity where you need to. You try to keep those so you're not running too low pressure and overheating that compressor.
So if the compressor goes down, all 3 coolers.
Yeah.
Why don't they run separate?
Well, they do usually. Where we see a lot of unloading is in rack application parallels. So you'll see on bigger systems though where they have 2 compressors or 3. Anytime you're using staging, a lot of times your staging will also have unloading. So what we see a lot more now is more variable speed, which we'll get into in this class. So pressure capacity drops to 10 horsepower, suction pressure is maintained. So if they all satisfy, then obviously the compressor pumps down, shuts off. Any questions on that? That's pretty baseline unloading when you get into mechanical unloading. Now, if we're doing electronic unloading through like a controller, that's going to be different. This is just off of mechanical switches. So low pressure controls. So we're going to show you a cutaway of a Copeland compressor and a Carlisle of how the unloader works inside. So you guys can kind of see how that's working when that energizes and de-energizes that cylinder coil. So the cylinder is loaded, it is pumping refrigerant vapor efficiently. So this is a Copeland. It's going to be a reed valve style. It's just based on the graphic. So like an LAC or a K-body, or this is the type that they're talking about. So not to be confused with a discus. So you've got your suction pressure that comes in. It's going to feed through just like it does. You guys see that little bit of clearance between the reed valve and the piston? Right here on the, let me show you. Can you guys see that cursor?
Yeah.
On the screen. So here's your high side reed valve, and then here's your clearance. That piston's going to come to the bottom of that clearance right there. So you have all this area where discharge pressure still resides, right? What happens on the downstroke, if this is like a 12-to-1 or a 10-to-1, that pressure has to fill up the volume, the area in this cylinder to drop low enough that the suction pressure overwhelms that and pushes more new vapor into the cylinder. Okay, that's why compression ratio is so important, because if you have a really high pressure, it's going to take more space, more volume inside that cylinder before that suction reed opens and allows new gas to come in to absorb the heat in that compression. You understand that? And so this is why if it's really high and really low, you don't get a lot of new vapor per stroke, per downstroke. It becomes very inefficient, number one, and you don't get the heat absorption you need through that process of compression, because we're still absorbing heat there in that compressor. That's why we need cool vapor there, so that we can absorb that heat and take it outside. Okay, so that's why that compression ratio is so important. It's because you still have high side gas in that stroke. And so on that downstroke, the higher that high side gas is, the more space it needs to equalize to the suction pressure. Does that make sense?
Hey, Jim, your pointer is not visible, just to let you know.
It's not? You guys can't see that? I'm sorry. Let me see if I can fix that. Can you see that now?
I got nothing. Yeah, no, I got nothing.
Where is that at?
I can see your white cursor, Jim.
Yeah, it's just really small.
Yeah, it's real tiny.
Okay.
Real tiny. We can see
Can
it.
you see?
Oh, I got you.
Can you see? I'm by that red arrow. So can you see that compressor, that discharge reed right there?
Yeah.
Yes.
So if you guys have ever pulled a valve plate and you've seen that discharge reed is quite a bit more robust than the suction reed. So it's under spring pressure. It takes a lot of pressure to push up on that reed and open that up. So when you guys have discharge feedback, when you isolate and you check those valves, that's why if you're getting any pressure coming back into your suction side, that's why you have bad valves. It's because that reed the integrity of that reed has either broken or for whatever reason is not seating, and you're getting hot discharge gas in the other side, into the suction line, okay? So right there where that reed is from, where is that cursor? From that reed to the bottom right there of that casing, that's your cylinder wall. So the piston's only gonna get clear to about there. So you have all this area right here, discharge gas still in that cylinder for the downstroke.
I have one question.
Yeah.
When that solenoid valve de-energized, it pushes that spring down on that, it pushes that black part, that spring down to close that suction line off. It closes off that suction line right there from vapor going into that piston.
Correct. It's going to shut off the suction line at the head coming into the compressor head. So we'll go through that in just a second here.
Now my
so the coil energizes. Go ahead.
Does that piston stop moving once that happens?
No. Oh no. It's that's why they call it unloaded. The piston continues to move off the crankshaft. Nothing happens from the crankshaft and the pistons. What happens is we take the load off of that head. So as you can see right here, we stop that suction flow. So there's no vapor to compress at this point. So it just freewheels. So whatever's still loaded is the only thing that's compressing at this point. So on that graph, go ahead.
Okay, so it still moves no matter what.
Yep.
Okay.
Yep. That's why when you've heard these things unload, sometimes they make an awful noise. Right? And that's them. They rattle a little bit when they're unloading on those reciprocating compressors.
Gotcha.
Okay, so this is just going to be the same thing, but Carlisle's a little bit different, same concept. So this is a Carlisle unloading compressor. So it's going to do the same thing. Coil de-energizes. The solenoid energizes, the suction port is blocked, the cylinder is unloaded. So coil energizes, blocks the suction again. So that piston continues to pump. So, but what it doesn't do is if there's no pressure on that valve on the suction line, that valve never opens. So that piston just freewheels, not compressing anything while that's energized. When it de-energizes, it loads it back up.
Okay.
Any other questions? Okay. So compression ratio is head pressure in PSI absolute. So in suction pressure in PSI absolute. So as suction pressure decreases, compression ratio increases, and discharge vapor pressure or temperature increases. So high compression ratio is high discharge temperature, and there's your maximum. That 12-to-1 is where manufacturers start to say you're probably going to get some breakdown. You're probably going to have some problems. So it's too much heat. So oil in the cylinder smokes at 300 degrees Fahrenheit. So. Hey, can somebody mute their phone?
Hey, I'm sorry, Jim. Let me step out real quick.
Okay. So here's a graphic for compression ratio. So if your suction pressure is at 83 and your discharge pressure is at 275, you have a 3.3-to-1. That's a healthy compression ratio. That's good all day long. So your discharge vapor is at about 175 at that point. I'm assuming this is for R22. So as you see that suction pressure drop and your head maintain, you see how it absorbs less heat, your discharge pressure continues to go up. again, you're getting less volume per stroke is what it comes down to at the very baseline level is because you're filling that cylinder, you're having to satisfy the volume in that cylinder, and the pressures have to equalize before that suction reed overwhelms and opens up and allows more cool gas to go into the cylinder at the compressor. So here's an evaporator at 40 degrees. Compression ratio is at 3.3 to 1. Discharge is 175. So if we use the compressor for low temperature, the evaporator is at negative 20 degrees. So the compression ratio now changes to 11 to 1. We're getting close. So discharge pressure increases to 280 degrees. So if you use it for extra low, the evaporator is at negative 40 degrees. Now we're at 18 to 1. Your discharge is 320 degrees. At that point, we're cooking oil. Okay. Copeland's max discharge. Go ahead.
That's when you also need your head coolers and
yep. Desuperheating, liquid injection, demand cooling, depending on the manufacturer, they all call it something different. All does the same thing. So we'll talk about that here. It's on the slide deck. So we'll definitely talk about, liquid injection and, desuperheating and demand cooling. So Copeland's max discharge is 225, and that's you guys are going to measure that with a clamp 6 inches off the compressor. So if you guys ever want to know if you're running too hot, take your clamp, go 6 inches off the compressor on the discharge line. If you're clocking 225, you might want to figure out what's going on. So your either compression ratio is too high, not getting enough cool gas to that compressor, bottom line. Okay. So that's when you can checking that superheat reading on the front side. Hopefully helps with that. That's where you're shooting for that 20 to 40 degrees on the compressor superheat. So you're going to do the same thing. Come 6 inches, gauge up to the suction king valve, go 6 inches up with your clamp, look at your superheat there. That's where you're going to see what you're getting there. Okay. Carlisle is about 250. So has everybody seen an enthalpy chart? Everybody know how to read an enthalpy chart? Okay, so what this is an enthalpy chart. So what that tells us is our refrigeration effect. You got your enthalpy, which runs across your BTUs per pound, the type of refrigerant. So your saturated liquid to your saturated vapor. So we'll go over the lines real quick.
Hey, Jim.
Yeah.
Hey, sorry it took a bit to get this off of mute. One thing that I have run into over this past 6 months, a lot of the or not a lot, but some of the Copeland condensing units that are now coming out with essentially the Dixell controller, they've got a thermistor located on the discharge of that compressor for compressor protection. One of the things that we're finding is on this particular application, the original condensing unit was actually oversized, which wasn't noticed until we swapped the condensing unit on it and then started running into problems with a high discharge pressure. So we really had to decrease our superheat a little bit further than what it was. And we actually tied 2 of the evaporators into one condensing unit to compensate because it was a compression ratio issue.
Yeah, it's great. Do you know, Sean, on that note, I know that Copeland was trying to come up with a way to predict slugging or flooding too. So is that controller doing that as well? Looking at that point of reference? So, because if you're looking at a low discharge and you're looking at if the discharge drops too low, does it have anything on the suction trying to measure superheat, or is it just discharge temp? I lose you?
Can you hear me
All right,
now?
we'll come back to that. Yeah, there you are.
All right, sorry. The only thing they've got on the suction side was pressure, just a pressure transducer, just for monitoring, which would also include the low pressure cutout. So. Yeah,
we sat in a thing last year that was actually they're wanting to come up with a anti-slugging flooding control, and I know that they want to tie it into that Dixell controller since they purchased them. So I didn't know if it had hit the market yet, but we should start seeing that pretty soon here in the field. So anyway, that top line, guys, that's your condensing. So the bottom line is your evaporation. Your angled line right there is telling you what it is. It's your compression line. So let me ask you this, just by looking at this, if you guys understand this, where are we picking up that extra heat to raise up that? Why is my discharge increasing? Do you see how the line's getting wider for the stage of compression? And if we're temperature pressure related. So we're running a little bit, go ahead.
We're getting lower capacities on the lower temperature.
Yeah, we are. Yeah, and refrigerant wants to continue to just keep absorbing heat energy. So it's going to continue to do that until we start to desuperheat, under pressure, we start to cool it. So, and then it'll start to try to give off that heat instead of absorb that heat. That doesn't happen until it hits that condenser and it begins to desuperheat. So even though the line's hot on the discharge line, it's still that refrigerant's still trying to pick up any heat it can. We still haven't began to desuperheat. We don't start to desuperheat till we hit that condenser. And so all the way through the evaporator, all the way through the heat of compression at the compressor, all the way up till it hits the condenser, it's trying to still absorb. At that point, when it starts to cool under pressure, then it starts to give off its heat. That's when it starts to actually give instead of absorb. So if you understand when it's supposed to do what it's supposed to do, it'll help you understand why we're still gaining heat and why we're not cooling our compressor. Because if it doesn't have a lot of heat absorption property, because we don't have the volumes there we need of the refrigerant, because refrigerant will only absorb so much heat per pound. That's what enthalpy is. So if there's only so much vapor in there, we can only absorb so much. That means the heat continues to remain at the compressor, and then it adds up and it adds up, and so then you're not adequately absorbing for the size and the tonnage that you're dealing with. That's what's going on. That's why it continues to overheat. So, and when we're dealing with minus 40 degrees, I would hope you guys are seeing some controls. It's not going to we're going to have some kind of desuperheating mechanism there, and some oil coolers, some head fans, whatever we can do to keep that compressor cool. If we're dealing with anything more than, a 10 to 1. Again, they're shooting for more like a 3 or 6 to 1 compression ratio is what your manufacturers are shooting for. They don't like. You start flirting with it when you get up in the 10s and 12s, especially like the 15s and the 18s. So using two-stage compound systems, 2 compressors in series, compressor 1 discharges into compressor 2. A desuperheating valve cools the discharge vapor. So I'm trying to think where we would see this in application, if anybody can speak up. I've seen it a few times. So you got your suction coming off your evaporator at negative 40. So it's coming into your first compressor. It discharges out of the compressor at 180 degrees with that. So, and then you've got what's called here this desuperheating valve. And what that's doing is it's metering, just like a TXV, saturated vapor into that discharge line between the compressor and the suction line into the second stage. So what that does is as soon as it hits, go ahead.
No, I'm just looking. I guess that's used to cool off the hot vapor coming in from that first compressor into that second one, so it won't be that suction line of that next compressor. I've seen it in a carrier. Yeah, in an AC unit. Yeah,
there is applications out there. I just can't think of one off the top of my head. So I've worked on them too. So yeah, so what it's going to do is it's going to meter in what we need to keep enough cool gas based on that compressor's manufacturer spec. Make sure we keep a good close compression ratio. So 65 to 275, you see how the compression ratios are the same, where if we tried to take a negative or close to the same 4.3 to 1 and 4.2 to 1, that's healthy, right? That's good volume per stroke. So if you try to take that negative 40 over to what the discharge is on this 180, that would be worse. It would actually be a lot higher than 180 also. So you would be dealing with more like we saw on the last slide on R22, we would be dealing with like an 18 to 1. which you would smoke the compressor and the oil.
Now, by having two compressors like that, with that one evaporator, what that actually does help to bring down the temperature in that evaporator quicker. You have two compressors like that.
Yeah, it would on capacity. I think on that, with that running independently, it's really meant to yeah, no matter what, it's going to run it more efficiently. The closer you get those compression ratios, systems are going to run more efficiently. So we used to, back in the 90s and early 2000s, we were dealing a lot with compression ratios and floating, and bringing down Albertsons used to bring down their head pressure to like 130 on R22, which that created other problems with stacking refrigerant. I mean, everybody was trying to come up with ways to tighten up that compressor. I know that Kroger runs really high suction pressures historically because that helps their compression ratios. They get a lot of energy savings every year off of running their suction. So I got a question for you guys. What do you think would be a better strategy, just in talking to this? Dropping your head or raising your suction? Where do you get the most bang for your buck?
Dropping your head.
I would say raising your suction. The smaller number, if you only raise it 10 degrees, it's gonna really make a difference. If you raise, or 10 psi, if you raise it 20 psi, if you raise it, you're gonna get that compression ratio a lot closer for every degree on that lower number. So you can drive that head. You can only drive that head down so much too before what happens if you try to drive your head down too low.
You go static on your valve.
Yeah, you don't get your pressure drop across your metering device, or it struggles with it. And what happens in the wintertime in you cold regions?
Your refrigerant
Yeah, you're going to stack a lot of refrigerant to get, because if you're dropping that pressure that low, your headmaster or your holdback valve is not going to start letting stuff through until you almost plug that whole condenser with refrigerant. So if you got to fill that whole condenser with a lot of refrigerant before you can get down to that low pressure and start metering through. So what we found when we ran that head pressure down too low is we held back way too much. It just caused a lot of problems. So, error on the side is if you guys get into more rack balancing and really taking care of your customers on a supermarket level, see what you can do with that suction pressure without compromising. This is why they're doing glass doors, guys, on open face cases. This is why they're doing a lot of that stuff, because you can raise that suction pressure if you have a glass door case, right? And you can go to smaller tonnages and you can get a lot more energy efficient at the rack. More volume per stroke, less runtime, longer life cycle on your equipment. Okay. A single stage has a high compression ratio. Suction at 15 psi is raised to 275. That's at 18 to 1. If you ran it straight across with a single stage. So by running it on two stage, what do we see on those? 4 to 1, 4.2, 4.3. So stage 2 suction to 65, raised to 275. You get that 4 to 2. So the discharge goes to the condenser. So this is that same chart if we were doing single. Now if we do a two stage, it's just saying the same thing on an enthalpy chart. Guys, if you don't know how to read an enthalpy chart, let us know. We'll do a class on enthalpy. So it's important that please.
Yeah.
Okay, I'll make sure we get it on the schedule so you guys understand enthalpy, because it's important when we're talking about, especially in these specialized class, we talk a lot about heat transfer and heat load and energy. And so just getting down to the really basic building blocks of why we do things, why we strategize, why manufacturers are doing what they're doing right now is based on these metrics that we're getting. So as you can see what happens when you guys go to a two stage, look at how much it shortens up my heat of compression line. It almost cuts it in half. You guys see that?
Yeah.
So all that extra heat that I'm picking up, I shorten that up with my compression. I'm getting more vapor per stroke. So I'm getting more cooling properties, heat absorption, right? And so that's where we're getting those savings, getting that value. Any questions on this, on the two stage? Okay. So a single 2-stage compressor, one large compressor instead of 2. So first and second stage within one compressor has 3 heads or sets of pistons. You guys anybody here worked on a Carlisle compound? I have.
Yeah.
Husman Super Plus racks. Anybody worked on a Husman Super Plus rack? Carlisle compounds. So that's where we've seen them. So we've seen them on a couple polar racks too. So 2 heads discharge into the suction of the third. Ultra low temperature 2-stage compressor. So you got what you see is your evaporator, your suction line comes into those 2 heads on the low side at the head. So that vapor comes in right at those 2 heads. It compresses on that first stage, comes right out of the heads and goes into the bell end on that inner stage. As you can see, again, we have the desuperheating valve in that inner stage. Okay, that's to make sure we have adequate vapor there to continue to absorb through the heat of compression process. So it comes in through that bell end and then goes out on that one. So the discharge line on these compressors will come out of one of the heads. I'll have a king valve on that high stage. The suction actually will pipe into a king valve right in front of, and then split off into the low stage. So, and then it'll pipe off the back side of those 2 heads, key in and pipe into the bell end of the compressor. So you take that negative 40, 60 degrees, you go through the low stage, you discharge off at 180, you're desuperheating the valve, mixes with that discharge gas at the inner stage. The inner stage goes into the suction bell end, comes off at the high stage at 180. So, and we achieved the same thing we did with that 2-stage system within one compressor. This is a picture of a Carlisle compound. You guys haven't seen one. I love these compressors, by the way. They're pretty robust. They're heavy as heck, yeah. So you got your discharge valve there. Like I said, they're both there on the front. So obviously the piping's a little bit different than what we're used to on your traditional compressor, your refrigerant cooled compressor. Okay. So coming from the condenser, you have your suction king. Nice to work on because you got your 2 king valves right there on the front. So suction comes in, goes through that first stage or the low stage. So hits that manifold, goes into your inner stage. So flip it around to the back. You'll see that's your desuperheating valve right there, tied into your inner stage. That's where it's mixing. So goes in to your inner stage and then compresses like a normal compressor. It comes up through the crankcase into that second stage or that chamber there inside the compressor with no external piping, and then discharges out your discharge valve. Demand cooling. Demand cooling is a control we see on Copeland. So Copeland came up with demand cooling years ago. What happened was they started using R22 a lot on medium and low temp application because R22 and the pressures it runs a really high compression ratio. So if you guys are in any old markets, we used to be able to just eyeball by walking in the store. We could tell the low temp from the medium temp rack by the controls and head fans that were on them. So we still see that a little bit with the 404 racks, but because you still have a pretty high compression ratio. But with R22, it was real simple. So low suction causes high head temperatures. Sensor and head activate solenoid valve. Valve injects refrigerant into suction. So suction's raised, head temperature is lowered. I'm sure everybody has anybody not seen this?
Old style.
Don't be afraid. So so that is not a demand cooling valve. That is a flaw. So the temperature sensor, that's actually a head pressure control with a manual reset. The temperature sensor, if you guys can see my cursor, is right here. Okay, right there at the top of the head. So there's your injection valve. Goes in and flashes the chamber right before compression. So any questions on demand cooling? Hey, can anybody remember? I couldn't remember and I didn't have time to find it. What temperature does demand cooling kick in at? Does anybody know for sure?
Say
It's
that
like
again.
250 degrees.
Is it 250? The demand cooling starts injecting liquid?
Yeah, I think it's 250 degrees.
Okay. I'm going to spot check it just to be sure, and I'll come back next week on Thursday and make sure that we have those specs. When it starts to, and then at what temp, do we know what temperature it locks out at?
I don't.
Okay. Yeah, I'll get that for you guys. That's important information to have. So when we're troubleshooting those. So Copeland Ultratech scroll compressors using high efficiency air conditioning. Has anybody seen these scroll compressors with the unloader ring on AC? I have. I've worked on a few of them. So what it is it's 100% capacity is only needed at high loads, ambient 95 or above. So this is one of the, so if you're dealing with a high efficiency unit and there's a couple extra wires going into your compressor other than your line voltage, those wires are going into a speed of solenoid inside that actually shifts a unloader ring inside that top of that scroll that drops at 33% load. So low load ports opens to utilize less scroll area. Compressor operates more efficiently, prevents short cycling, better humidity control, lower operating costs. So here's it at 67%. So that's just your basic how a scroll works. Those two rotors oscillate, and that's how they compress. Discharge valve is in the middle of the compressor. It pushes that gas towards the middle and up through the discharge valve. So when the solenoid opens ports, so it opens up to and drops capacity by 33%. So there's two little holes in there where it's bypassing the discharge valve. So in the passes. So as those two discs oscillate, so it opens up two ports. That unloader ring, what it does is it slides really ever so slightly one direction and opens up those ports. And then when you de-energize it, it's spring loaded. It returns back to plugging those two ports. Digital scrolls. Anybody dealing with digital scrolls?
No.
I know we're dealing with digital recips. We got them at a couple of our Costco's on the Bitzers. You guys seen those yet? Anywhere in your markets? We have Spanish Force got digital, don't they? Does Pocatello have digital recips, Sean? Oh, that's Carlisle. Okay. So yeah, Copeland and Bitzer have been they have digital reciprocating compressors now. So on low load, a solenoid valve opens, injects discharge vapor into the suction, raises the top scroll, and to stop pumping, this unloads the compressor. I'm sorry, not digital. Variable speed. My bad. So scratch that. It's variable speed. Variable speed. I know, variable speed recips. I'm like, that did not sound right. So, okay. So adoption of the Copeland digital scroll capacity control. So Copeland's pretty proud of this because scroll technology, they say, is the future. I'm still on the fence about it. I'm still a fan of semi-hermetic. So, but it is a cool compressor. These digital scrolls, you'll see a lot of modular rack systems, smaller rack systems, and small applications, C-stores, smaller markets, like your Trader Joe's and some of your protocol systems. They'll use first stage with the digital scroll to be able to continue to keep that rack running and then just ramp up the capacity up and down. So pretty much the same concept. It's just bypassing it right into the suction line through the solenoid. So scroll separated, no compression. So it separates the scroll and then it dumps that discharge back to the suction to equalize it, and it modulates that way. The reason why they call it digital is because it's on or off. So they can modulate through that down to 10% capacity.
I have a question.
Yeah.
I went into an Albertsons one time, and I was so used to looking for the rack, looking for a big old room, and the whole rack system was just up on top of the walk-in in a box. The compressor was like
Yeah,
in
the
a
Protocol.
that's a modular, so that's what we're talking about. Those smaller, like Protocol is the famous one from Hussmann, but I think every manufacturer now has some type of modular rack system. So I'm sure a lot of guys have very much a hate-hate relationship. I mean, love-hate relationship with Protocol. So, but yeah, we've dealt with Protocol for years.
Yeah,
So,
yeah. It's been a while. The first one I seen was up there by Red Rock. And I was like, "What the heck is this in a little box?" That was the whole rack.
yeah, so you'll see in a supermarket application they'll place those in different places in the store. I know Sprouts uses a modular. We've seen them at some of the Associated Foods. We've seen them at some of the and C stores are starting to adopt modular rack systems. So multiple compressor racks. So we're going to talk some parallels. Compressor cycle off or on as load demands. As load decreases, suction pressure or decreases. So low pressure control cycle compressors. That is kind of old school. So low pressure control is very rarely now cycle compressors on a rack. Most of the time they have a controller. So it's going to be an E2, it's going to be a Danfoss, it's going to be microthermal, it's going to be Opto 22. So it's going to be some kind of logical controller that's doing a PID staging. It's actually a learning algorithm within the controller that's actually learning based on load and capacities and staging compressors. So we talked about Copeland. These are Bitzers. Those ring compressors on the rack. I don't think we have any slides on the Bitzers. If you guys want to know more about Bitzer, I can do a class just on Bitzers if we're seeing a lot of Bitzers out there. You want? Okay.
Oh.
Yeah, I know we have a lot of Bitzers out there. That's why there's nothing on Bitzer in here. I went through it, but if we want to spend some time on Bitzers, maybe we can compile Bitzers and CO2 together, talk about both, because Bitzer's really hanging their hat on that natural refrigerant market. So.
Oh, that's Winco.
Yep, and Costco and a couple others. We see a lot of Bitzers making some ground for sure. They build a pretty good compressor. So sensors in the suction header. So send signals to the control panel, which cycles the compressors as needed. That's what we were talking about. So hot gas bypass, hot gas valve opens on a drop in suction. I looked at this last night. I might hurry through this stuff unless one of you guys have seen this application. Hot gas raises suction pressure, prevents high compression ratios, prevents compressor short cycling. Has anybody seen where they're dumping hot gas into the suction?
Yeah.
Where do we see that at?
Fred Meyers have it. Some of the Fred Meyers
Okay.
here.
Okay.
This was a previous company that I worked for that I seen it on the Fred Meyers.
Got you. Okay. So, like I said, everybody has their way of trying to tighten up their compression ratios. So, Fred Meyer is doing a hot gas bypass into the evaporator. So,
I know I noticed on, what is that on those, on those fallout ice machines? I had thought that was like a water-cooled condenser, but actually it's a condenser superheating the vapor going into the compressor. It's like a water-cooled condenser, and they're using that to superheat the vapor going into the suction side of the compressor that way on them faucets, on them Tecumsehs.
I'll have to look at that. I'm not familiar with that. Anybody else familiar with that?
They on the Circle K's out here.
Okay. Yeah, I'll have to look into that and circle back with you guys on that one. So I'm not really familiar with that. So same concept. So we're dumping hot gas through a discharge bypass valve that's a modulating valve with an external equalizer. So it's looking at what's coming out of the evaporator, and it's using that external equalizer to modulate how much flow it allows into that distributor coming off of the TXV. You guys all see that? Hot gas section 9, hot gas is injected in your compressor, desuperheating thermal expansion valve cools, gets hot. Hot gas to suction line uses desuperheating valve, sorry. So it opens based on demand, sends it through the discharge bypass valve, the desuperheating valve mixes with that, and then heads back to the compressor. And all of this is to help the compression ratio.
It also helps with capacity too.
Well, yeah, that's what it is because again, remember capacity drops, and we're trying to. So what the compressor manufacturer is trying to do is cycle 6 times, and then when it is running, keep its compression ratio in range.
Yeah.
So it's doing both. So by increasing that capacity on low load characteristics, it's going to start to bypass through the desuperheating valve and the discharge bypass valve, and it's going to mix that vapor to get that compression ratio up so that we get that satisfactory compression ratio of the compressor. We get it the cool gas that needs to stay alive, and at the same time we keep it running so we're cycling 6 times or less. So here's VFDs. So capacity control by slowing the compressor. So in the US, motors run at 60 hertz frequency. So lowering the frequency will slow the motor. Slowing the compressor will lower its capacity. So variable, here's your VFDs. Adjusting motor speed at the load. So 60 hertz is at full speed. So right here, we're at 48 hertz. So is there anybody that hasn't seen how a VFD or a VFD application in the field yet? We use them a ton in our markets. So you'll see them. So like you'll see them on our compressors at some of the Costco's. You'll see them on the door, the door curtains. They're up above the door blower. There's VFDs there. There's VFDs on our condensers. I mean, we have tons of VFDs out there.
So are those controlled by the microthermal units?
VFDs, it just depends on the application. That's a really broad question. They can be if they're, if they're talking on the same, and Scott will talk to this tomorrow, but with any of your controllers, if they can talk on the same protocol, which is the language that it speaks on. So if you have a backnet VFD and a backnet controller, which Emerson talks on backnet, that's its protocol, then you can talk to the VFD. So if you have a Echelon controller, which is what Microthermal talks on, that's their platform, and you have a backnet VFD, they won't communicate with each other. So whenever you guys are actually trying to size for or trying to scope a job for application, that's the first thing you need to look at. If you're dealing with controls, you need to make sure that they're talking on the same protocol. Because if they talk on the same protocol, we can get it to work. We can work with the manufacturer, we can get it to work. But if you're talking on different protocols, they don't understand each other, they won't work. So, and the good news is more and more manufacturers are trying to go to an open API, an open protocol, so that they can talk to each other. So if you notice with Emerson controllers, they'll talk on Modbus, they'll talk on BACnet, they'll talk on Echelon. So and now Microthermal's new 700 series will talk on all those 3 languages as well. So we're getting there. We got some ground to make up, but we're getting there. So that's a long answer to a short question. Does that make sense?
Yeah, it did.
Okay.
I have a question. I want to get off the subject. On them scroll compressors that has that little hole at the top of it is that demand cooling as well for the refrigerant? On those scrolls,
the hole on the top.
It has a sensor bulb drop down the middle of the hole.
Yeah. Yeah.
That's demand cooling as well.
Yeah, so usually what you'll see is we'll hook up what's called a Y valve, and it's only called a Y valve because the model number starts with a Y. So, but it's a modulating valve, and it has a little, it's a mechanical valve, and you put the temperature probe down inside the top of the scroll, and then it modulates how much refrigerant it flashes into the chamber to desuperheat that compressor. So yes, it's the same. It's a capacity control. It's to help with the compression ratio and cool the compressor. So you'll see those when so just start to notice, guys, what applications they're using on. Usually you're going to start seeing, modulating valves, Y valves, demand cooling, desuperheating valves when you're dealing with low temp application with the higher pressure, like 404s, 507s, 22s that are running a high compression ratio or a high head pressure.
Thank you.
Your compression ratio gets way out of whack at that point when you're trying to run those low temperatures with that refrigerant.
Okay.
So the VFD is up to 60% capacity reduction. So the one thing that the reason why it only goes down to 40% is because if you try to run those scrolls any lower, they use a centrifugal type pump system that pulls oil up to the oscillator plates through the center shaft, and it has to rotate at a certain speed to pull that oil up. So if you slow it down too much for too long, you dry up the compressor. So anytime you're dealing with VFD control in a compressor application, you have to be aware of what the oil's doing. So because you can only slow down compressor so much, you can only do so much, because depending on how that compressor pumps or slings its oil or pulls its oil out of the crankcase, it matters how slow you slow that compressor down. So if you have a compressor, you make sure if you're dealing with a VFD compressor, you read the manufacturer specs on the minimum frequency run, okay, and the maximum. And that'll tell you the frequency you can run at and the maximum amount of time you can run it at that frequency. They have sheets on every compressor that's VFD compatible. You guys have any other questions? Man, I couldn't have been closer to 8. So thanks, guys. So if you have any other questions, like hit me up off site and I can send you more information. I can also send you a PDF of this PowerPoint deck. So some of these we have PDFs on if you want to review or have that, let me know. I'll send it to you. But that's a wrap. Have a good day.
Hey, thank you.
You're welcome.
How do I get off this? Darn it. Oh, leave the meeting.
everybody there?
Yeah, I'm here.
Okay. Okay, we're going to run through capacity controls. If you have any questions, just speak up. In the interim, if you could just throw your phones on mute so that it eliminates the background noise. We'll run through this. Capacity controls we use a lot in small format to large format markets and C-store applications. So we see it on HVAC as well. So compression ratios, the important key of capacity controls is the compression ratio. So what the compression ratio is if you guys take the absolute suction pressure and you do, or the absolute discharge pressure, and you divide it by the absolute suction pressure, so it causes, that's your compression ratio. So low load causes low suction pressure. So, you know, at night in the cooler months, if the doors are shut, that causes low load situations. So that low suction causes high compression ratios. So as those suction drops, usually, you know, that head pressure increases. What compression ratio really gets down to is it's telling us how much volume of vapor refrigerant we're getting in every downstroke of the compressor during compression. So when that piston pulls back in the cylinder, can somebody mute their phone? I'm getting background noise, I'm sorry. So when that piston pulls back and that cylinder fills with vapor, so if you have a really high discharge pressure, there's always a little bit of discharge pressure left in that cylinder. So it has to expand and drop below the pressure in the suction in order for the suction to overwhelm the reed valve on the suction and fill the cylinder. So you know how quickly that piston's going up and down, you know, in cycling. So for every time it goes downstroke, if there's not heat transfer property there or less heat transfer property because the compression ratio is so high, it causes the compressor to overheat. Does that make sense? Heat causes compressors to fail. So heat and voltage are our highest failures for compressors. To protect compressors from low load, we use capacity controls. Unloading is a capacity control. What is capacity control? It's matching compressor capacity to the load. So if the load drops and reduces the compressor efficiency, it reduces compressor efficiency. One method is to reduce compressor pumping, block suction ports. We block suction ports so vapor cannot enter the cylinder. So this is called unloading. So we'll go over a couple slides on unloading. As each T-stat is satisfied, its solenoid closes, suction pressure starts dropping. Low pressure switches activate the unloaders. So, but that's low pressure mechanical switches. So just a regular low pressure control, it goes into the suction side of the compressor. As that suction pressure drops, it begins to energize solenoids on the head of the compressor to unload it. So here's a little example. We've got three walk-ins with 3 evaporating units in the walk-ins. We got a W body compressor with 3 separate heads and 2 unloaders. So hold on a second while I load up this graphic. So this is all three walk-ins calling all three of them needing refrigeration, all of them running. So we're running, all cylinders are loaded. So walk-in one satisfies on temperature, so which causes the suction pressure to drop. As that suction pressure drops, the low pressure control closes, energizing the suction or the unloading valve on head number one. So and drops that compressor from a 30 horsepower to a 20 horsepower. So then walk-in two satisfies on temperature. Same thing, a second low pressure control. So we have two separate low pressure controls for each unloader. So that pressure drops below, it still stays below head number one, and now it drops to a pressure below the set point on head number three. So compressor capacity drops down to 10 horsepower, and pressure is maintained. So what happens with these compressors is it never stops cranking. The pistons are still cranking, the crankshaft's still turning, but there's no load on it. So we stop the refrigerant flow from the suction line, and it's just freewheeling inside of the compressor. That's why they make a little bit of noise when they load and unload. System pumps down and compressor shuts off on a third low pressure switch. Copeland compressor unloader, the following slide shows normal operation. The cylinder is loaded. It is pumping refrigerant vapor efficiently. Here's a cutaway of a Reed style Copeland compressor. So if you guys can, sorry guys. Just gotta, can you guys see that little asking me if I need to record on your screen, or is that only me? Must just be me. So we have a cutaway where it's right now it's fully loaded. The suction comes in, the through the compressor head, down through the suction reed. The piston pulls back, compresses. So what you guys usually will see is right here between this discharge reed valve and the clearance for the piston, there's a little bit of a little bit of discharge gas that resides here. If it's at a really high pressure, when this piston pulls back right here into its downstroke, that high pressure gas has to fill up the volume of the cylinder to a point to where it drops below the opposing pressure of the suction pressure right here, in order for the suction pressure to push down on this valve and fill the cylinder with new cool gas. So if it's running a really high compression ratio, you don't get enough vapor volume per stroke here, so you don't get enough heat transfer through this process, and therefore the compressor overheats.
Hey Jim.
Yeah.
The screen is stuck on refrigeration training service R5 advanced refrigeration. Can you see it on my TV screen up there?
Let me see if I can fix that.
There you
Is that
go.
working?
Yes, sir.
Oh. Second. Sorry about that.
That works.
Is it moving on your side?
Are you moving the cursor?
I'm trying to switch the slide. Are you not seeing that?
No.
Is it moving now?
Now it is. Yeah,
Okay.
there you go.
Sorry
There you
about
go. Now it's,
sorry about that, guys.
no worries. Thank you.
So Copeland compressors unloading. As the load drops and the pressure drops, the pressure control energizes the solenoid. The suction port is blocked. The cylinder cannot pump refrigerant. The cylinder is unloaded. So this is the same cutaway that we were talking about now that you guys can see it. So that solenoid is going to energize. It's going to, I'm sorry, it's going to it's going to energize. It's going to lift up the port, and that pressure is going to push down on that plunger. So you see how on the cutaway, how it energizes the coil. It actually just pulls a piston up. It unplugs a little orifice. That pressure pushes down on that piston and closes the suction line. So from the discharge side. So because obviously if it was from the suction side, as soon as we pumped out this suction pressure, it would reopen. So that's why it's ported over, and that arrow is pushing down on that diaphragm or on that seat against the suction pressure. Blocks the suction. So, and this is when that suction valve closes and that piston just freewheels. It's pumping, but it's not pumping any vapor. So it's not doing anything other than running. So, and with it running unloaded, it takes less amperage to push that. So this is a cutaway of the Carlisle showing the same thing. So normal condition cylinder is loaded full capacity. So as you can see, the suction pressure comes in, pushes down on the suction reed, enters the cylinder. The piston pulls back on its return stroke, compresses on its forward stroke, and opens up and compresses it into the discharge side. So this is the coil de-energized. So the things to remember is with what state the compressor's in, energized or de-energized. So a coil energizes. So again, it pulls back that seat, pushes against it. The discharge pressure pushes down on that to continue to engage that seat. So on the piston continues to freewheel without any back pressure on it. Any questions on that? Compression ratio. So the compression ratio and discharge temp. Compression ratio equals head pressure in pounds per square inch absolute divided by suction pressure in pounds per square inch absolute. So suction pressure decreases, compression ratio increases, and discharge vapor temperature increases. So height, you guys understand why that is? Does everybody understand that? So you're picking up heat. From the time that your refrigerant leaves your metering device, your TXV, it's in absorption mode. So it's going to continue to absorb heat. The superheat measurements we take are to measure how much heat we're absorbing. That's why when you're taking superheat measurements of the evaporator, you're measuring how much heat pickup or heat transfer you're having at the evaporator. When you're measuring at compressor, we still need superheat. We still need heat transfer properties in order to absorb the heat in the compressor through the heat of compression. And so it's still in absorption mode. The refrigerant only changes from absorption mode to rejection mode at the desuperheating stage, which is within the first couple passes of the condensing at the condenser. So that's the first time it stops absorbing heat. So even though that discharge line is hot, it's still absorbing heat. So if you have less vapor per stroke and it's still trying to absorb heat, you get too much excessive heat per pound of vapor refrigerant flowing through that compressor, and you don't have adequate cooling properties. So you're not absorbing enough heat out of that compressor, so therefore the heat keeps going up, and your pressures keep going up and up. That's why high compression ratios are bad, because we need a certain amount of vapor volume per stroke in order to cool the compressor, and that is why everybody gets hung up on compression ratios. That's why compression ratios matter. So maximum compression ratio is about 12 to 1. So if you're dealing with 12 to 1, to make it easy, if you're 120 degrees discharge and you have 10 degrees suction, that's 12 to 1. Oil in cylinder smokes at 300 degrees Fahrenheit. So if you have an 83 degrees or 83 psi suction pressure and a 275 discharge pressure, you're running a 3.3 to 1 compression ratio. That's a very healthy compression ratio. So your discharge temperature is 175 at that point. If you drop your suction pressure and don't do anything with your discharge pressure, so down to 25, you go from to 11 and 1. Remember, the pressure doesn't change. So if you're gauged up to it, your pressure is going to stay at 275 but your actual temperature is going to change. So because you're absorbing too much heat and you don't have enough vapor there. So that's what's going on. Your heat transfer, your volume's low in your cylinder, and what's there is trying to absorb as much heat as possible. Therefore, what's passing through your discharge line temperature-wise is excessively hot, and your compression ratio is excessively high. So you guys want to be seeing a compression ratio of about between 3 and 6 to 1. So when you get in the 8s and 10s and 12s, you're flirting with damaging that compressor. So examples of compression ratios start with this is an R22 compressor for AC. Evaporator is at 40 degrees. Compression ratio is 3.3 to 1, very healthy. Discharge is 175. So if we use that compressor for low temperature, this happened a lot in the 90s with 22. So the evaporator pressure is at negative 20. It changes that compression ratio to 11 to 1. So your discharge temperature is 280. So if we're smoking oil at 300, we're getting really close. If we use it for extra low temperature, like negative 40 evaporator, compression ratio is 18 to 1. Your discharge temperature is 320 degrees. So now you've gone way over the limit. You're damaging that compressor. You're burning up the oil. You're breaking it down. So, question I like to ask guys when you guys are doing compressor startups, you need to do a compression ratio check. I mean, a lot of times, guys, if you're going out on repeat, the first thing that we always say is, oh, it's under warranty. Must have been a bad compressor. Well, I'm going to tell you this from the field: 9 times out of 10, we didn't do it. We didn't do a check down. We didn't check for the voltage, the contactor. We had a restriction, something, and we had an excessive compression ratio, which caused it to overheat. So we go out, we change it, we throw a new compressor in, and nobody checks compression ratios. I would dare say that probably only 10% of the techs out there check their compression ratio on a startup. It's a big deal. So manufacturers want them to see that in that 3 to 6 range. So Copeland's maximum discharge is 225 degrees, and that you're going to take that temperature 6 inches up the discharge line with a clamp. So if you're trying to tape a K thermometer or strap a K thermometer to it, make sure you're wearing gloves so you don't burn your hands. So, because in the summer you will. Carlisle's is about 250 degrees. Does everybody know what this is? An enthalpy chart? I guess the more important question is does everybody know how to read an enthalpy chart? If you don't know how to read an enthalpy chart, our last class, they asked that we actually have a class on enthalpy and how to read an enthalpy chart and how to work through this. I think it's super important, especially if you get into sizing and engineering. When you're doing sizing for your customer, we want to be able to read it and know what we need to do with it. So what that bottom line tells you is based on the refrigerant. This is your refrigeration curve. That curved line is your refrigeration curve, your refrigeration effect. So that bottom line is just telling you that it's R22, and that's your enthalpy is how many BTUs per pound of R22 of heat you can capture. So that line that's going vertical is your approximate pressure pounds per square inch absolute. So 275 PSI. That top red line that you see that just showed up, that's your condensing. That's your condensing line. So your bottom line, that green line, that's your evaporation line. And that angled line is your compression line. So on the straight down line, right there on your refrigeration effect, that is your, that's where it goes from a discharge to a liquid and then goes through your metering device somewhere in that black line on the way down from the condenser line to the evaporator temperature. So as you guys can see, where you're getting your increase is if you look at the length of the line exceeding in your compression line, that's where you're picking up your heat. If you see on that 40 degrees, your compression angled line is fairly short, so you get that 175. If you go down to 25 to -20, you see how much longer your compression line gets. So you're picking up a lot more heat during that compression process. So, and then if you go to a -40, that line gets even longer, and then you jump it up another 40 degrees to 320. So just that basic chart, as basically as it seems, really shows us where we're picking up that extra heat and why our temperature is increasing.
That's kind of like.
You have any questions on that?
That's kind of like the same thing you were showing us on the previous chart, right? Where if it's at -40, you're going up to 320 degrees.
Yeah, so this is just an enthalpy chart. So these, you have these are available to you when you buy refrigerant. It's on the back of a lot of the cases. It's in a lot of charts that we throw away with our parts. If you're dealing with the refrigerant circuit and you need to know enthalpy, it's important that you understand it, because if you do like a retrofit, you're going to need to know how that changes. How that's going to change your compression ratio, how it changes your mass flow, how it changes your interaction with the oil in the system. So you need to know those couple things. But the importance about enthalpy is like really understanding what this chart's telling us and where the actual heat pickup is taking place. So the reason why is that line kind of stays pretty consistent in the curve. So we're picking up about the same amount of heat at the evaporator, right? But then because we push out so far past that refrigeration curve, it pushes out that angled line through that heated compression. And so what's really going on inside that compressor is there's less vapor per stroke, and so what vapor's there is trying to pick up as much heat as it can, and it's overheating it. Does that make sense?
Yes, sir.
So two-stage compound systems. So we're going to go over two compressor compound systems and then Carlisle compound compressors. So if you guys are dealing with you hear a lot of different terms for these valves that are on these compressors: liquid injection, desuperheating valve, demand cooling. I'm sure I'm missing one or two names for it. It's all the same thing. What it is it's an interstage valve or desuperheating valve. And if it's desuperheating, if we say the word desuperheating, it tells us that it's in a vapor state, because if it's subcooling, it would be in a liquid state. So if we're desuperheating, we're cooling down the vapor in a vapor state. So we know that's good, because we don't want liquid as the compressor. So, and the other thing that we're telling us is we're cooling it down. So we're cooling down the gas in a vapor state if we're desuperheating. Two-stage compound system. You'll see it's pretty big. It's like a regular system, but your discharge gas is going into another compressor. So you have first stage compressor, your low stage. So where we showed that, where you had if you had a -40 going into one compressor with a 275, you would have 320 degrees, right? And you would have an 18-to-1 compression ratio. But doing it this way, you have a 4.3-to-1 compression ratio. So we're in that 3 to 6 range. We're in a happy place. So, and then they have this desuperheating valve between the two stages that really just sends saturated vapor, just like a TXV does into an evaporator, mixes it with the discharge gas coming off that first stage compressor to help cool to help give it enough vapor for the second stage compressor. So in the second stage, we have a 4.2-to-1 compression ratio. So you see where we went from an 18-to-1, now we went to a 4.2-to-1. That system's going to be a lot more healthy. It's going to run a lot longer. Make sense?
Yes.
Perfect. Comparing, so here's a single stage to a two-stage. It's going to kind of go what I just went over. A single stage has a high compression ratio, 18-to-1. Two-stage has a lower compression ratio. Stage 1 has a 4.3-to-1, and second stage has a 4.2-to-1. So discharge goes into the condenser, same as regular refrigeration cycle. So single stage compressor. There's your enthalpy chart. So again, that straight down line, that pressure drop, that's where you're going across your metering device. So, and then you're at -40, and you're picking up a tremendous amount of heat to that heated compression cycle. Difference in the two-stage system. You're cutting that cycle in half, which even does more effect. You don't go 9 to 1. You go all the way down to 4.3 to 1. So just by cutting that load in half or going two-stage, it takes you from an 18 to 1 compression ratio all the way down to a 4.3 and 4.2 to 1. So much better for the equipment. So every manufacturer, if you guys have ever been to a manufacturer's seminar on their compressors, the first thing they're going to tell you is cool gas keeps compressors alive. So that's what this is all about. Cool vapor, getting into those and having enough vapor there to absorb the heat necessary to keep the compressor cooled down. A single two-stage compressor, one large compressor instead of two, first and second stage within one compressor, has 3 heads or sets of pistons and valves. 2 heads are discharged into the suction of the third. Ultra low temperature two-stage compressor. So this is one compressor, 3 heads. So on that first compressor, 2 of the heads is your first stage. So, and it takes that vapor coming right from the evaporator, takes it through 2 of the heads, through a manifold, and discharges right off the top of the heads there. So nothing happens inside of the cooling of the compressor at this point. All of it's happening right there at the heads. So it goes into if you look at this, and I'll show you some pictures of a compound, they're coming up next so you can see what I'm talking about, but it goes into what's called an interstage. At that interstage, you still have that desuperheating valve. So we're still metering how much cool gas properties or volume that we're sending into that bell end of that compressor. So from there, it goes through the compressor and it discharges out the high side. Has anybody worked on the Carlisle compound? Okay, I've worked on quite a bit. They're very robust. They're great compressors. So, but they're heavy as heck. So, here's a picture of one Carlisle compound. As you can see, the difference is where the king valve would usually be on the back, where that interstage pipe is. The discharge, the suction king valve is on the front. You can see where it manifolds into those first 2 heads, and then manifolds on the discharge out of those first 2 heads into the interstage pipe that goes into the bell end of the compressor. So you've got your discharge valve to the condenser. You've got your suction king valve coming into the compressor through stage 1 to low stage heads. Goes out on the manifold to the interstage to the bell end of the compressor. We're going to flip the compressor around. We're looking at the back side of the same compressor. You see that interstage. Suction goes through those 2 heads into that manifold, comes out on the interstage. This is where our desuperheating valve comes in to play. There's usually a temperature probe on the discharge line for these. And then as the discharge line gets too hot, it continues to inject liquid into saturated vapor into the interstage. Goes into the bell end, cools the windings just like a traditional refrigerant cooled compressor, and then goes through that second stage or high stage, and then discharges out of the compressor. Does anybody have any questions on this? Don't be afraid of these compressors. They're actually a lot of fun to work on. So, demand cooling. So, demand cooling is Copeland's kind of desuperheating system. Using some single stage compressors, low temperature applications, or one compressor with multiple loads. So low suction causes high head temperature. Sensor in head activates solenoid valve. So valve injects refrigerant into suction. Suction is raised, head temperature is lowered. So There's your demand cooling module. Usually if you have to hit the red button, you're low on refrigerant, or for whatever reason, it's not cooling. This valve right here, if you guys can see my cursor, that solenoid is what is injecting that saturated vapor right below the head so that it mixes with the refrigerant here, immediately vaporizes into a low pressure vapor, but it gets us the volumes we need. It raises the pressure in the crankcase to get our compression ratio to a more tolerable state, fills that head with that cylinder wall with a good volume of refrigerant, and then rejects it out the discharge line. So demand cooling head temperature sensors, that is not a head temperature sensor, by the way, guys. That's a flaw. That is a head pressure control with a manual reset. Where the head pressure, if you guys can see my cursor, that's your sensor right there. There's a little port on the top of the head that you'll take out on install. A lot of guys Teflon the threads, which I do as well. And then we thread that into the head, and that sensor plugs right into that demand cooling module and tells it the internal temperature of the discharge head right there. So as it senses that temperature, it opens and shuts the valve accordingly, that demand cooling injection valve. Copeland Ultratech scroll compressors used in high efficiency air conditioning, unloads to 67%. This is used in HVAC a lot. It's the scroll compressor with the unloader ring on it, drops it down 33%. So ambient at 95 or so 100% capacity is only needed at high loads. At ambient 95 or above, or high indoor heat load, low load port opens to utilize less scroll area. Compressor operates more efficiently, prevents short cycling, better humidity control, lower operating costs. So this is a top view of the oscillating plates for a Copeland scroll. So at full load, they put a couple ports in there, and that's what that unloader ring does, is it opens and shuts those ports. It covers the ports, and then it opens the ports. So when the solenoid opens, the ports, 67% of the scroll is utilized. It lowers the capacity by 33%. Any questions on that? Has anybody ran into that? Just no. I ran into them a bunch. So mostly you'll see them on high efficiency split systems. I've seen them on some rooftop units as well. Digital scrolls. So for medium and low temp applications, various capacities from 10% to 100%. So on low load and solenoid valve, on low load, the solenoid valve opens, injects discharge vapor into the suction, raises the top scroll to stop pumping. This unloads the compressor. Where we see these guys is on a lot of modular rack systems. We've seen digital scrolls. So the other reason for modulation is that compressor manufacturers only want their compressors to cycle 6 times an hour. So on and off. So they use these controls to keep the compressor running because it saves in energy from the load on start. So that high pull on start to keep the compressors on and off. So there's energy savings in that, and there's energy savings in tightening up that compression ratio. That's the 2 biggest reasons why we use capacity controls. So the solenoid valve de-energizes, discharge vapor to the condenser. It's just like a side cutaway of a scroll. So scroll separated, no compression. It energizes and bypasses discharge into the suction and unloads it down to 10%. So multiple compressor racks, parallels used primarily in supermarkets. Compressors cycle off or on as load demands. As load decreases, suction pressure decreases. Low pressure control cycle compressors. I would be shocked if you still see low pressure control cycling compressors. Most everybody is using an EMS type controller or a rack controller to cycle off the header pressure. So parallel rack systems. You've got, if you guys have ever worked on these, so it's pretty self-explanatory. You've got a sensor in the suction header, transducer. Sometimes you'll have temp sensors depending on the strategy. So it'll send it to the controller, an E2 controller or Danfoss controller or a microthermal controller or Novar. I'm sure I'm missing a couple. Which cycles the compressors. So as it'll stage that compressor up based on what the suction pressure is, the transducer in the header is telling it. That's how it stages those compressors. Hot gas bypass. Hot gas valve opens on a drop in suction. Hot gas raises suction pressure, prevents high compression ratios, and prevents compression short cycling. So here's your basic pump down refrigeration system. So if you add a hot gas bypass in there, you're going to add a solenoid, and you're going to add a discharge bypass valve with an external equalizer. That external equalizer taps into the suction line coming out of the evaporator. So, and that tells it as the suction lowers and raises, if the solenoid's energized, it'll modulate that discharge bypass valve on how much discharge gas it allows back into the evaporator, so it doesn't get too excessive. That's the reason for. So this is a total mechanical valve. So we have electronic valves that'll do the same thing. Hot gas to suction line. Hot gas is injected into the compressor. Desuperheating TXV or TEV cools hot gas. So this is also bypassing discharge gas, but it's also using a desuperheating valve to kind of mix that vapor to make sure that it's getting more cool gas from the suction line. Or I'm sorry, from the liquid line into the suction line.
Hey, Jim.
Yeah.
Hey, do you have a preference on using the mechanical or the electronic?
I only have a preference based on it, people that are able to repair it. So the serviceability of mechanical valves always seem to be easier for the guys in the field. Anytime you go from mechanical to electronic's always going to be more efficient and more finite in its readings. So if you're comfortable with electronic, go electronic. But if you're more comfortable with mechanical and you feel safer doing the mechanical, it's all field preference. But I would always, if you're not comfortable with electronic, get comfortable with electronic. Find like Dixel or some of these small standalone controller type systems, these little Dixel controllers, they can do a lot. So if you get used to using the Dixel control or one of those types of controllers to do these types of capacity controls, it's going to be better for you in the long run, because that's where the industry is going, and they're going that way because it is more efficient and it is more accurate.
Okay. Perfect. Thank you.
You bet. So capacity control by slowing the compressor. So we're going to talk about VFDs, guys. So I'm sure everybody's seen a VFD. You know, everybody likes VFDs. A question that came up last class is, you know, can VFDs talk to the controllers? And the answer was, if it's using the same protocol, then yes. If not, it's usually an analog input from the controller that can ramp it up and down. So most of the time, you'll see the controllers just use an analog output or input to kind of send the signal to the VFD to ramp it up and down. Based on the analog input that the VFD receives from the controller, it starts to adjust. So it's not a very finite adjustment. It's very broad, but it works. So that's kind of what you'll see out there now. But if you get like an Emerson drive and an Emerson controller, they're going to have a program in that controller to be able to drive very effectively and very efficiently. So if you guys are sizing stuff up, make sure that you size to, you know, the same protocol type equipment. So if you're using like an echelon, which is microthermal talks on echelon, then you're going to want to have a drive that talks on echelon. If you have a backnet controller, then you're going to want a drive that talks on backnet. If you have a Modbus controller, then you're going to want a drive that talks on Modbus. So you just need to understand what protocol it talks to, so that you know how to line up your equipment so that you get the best bang for your buck. So in the US, motors run it at 60 hertz frequency. Lowering the frequency will slow the motor. So you can't do this with just any motor. You need to have one that, you know, is rated to be tied to a VFD. Slowing a compressor will lower its capacity. Obviously, less cycles on the pistons, less capacity. Has anybody not seen a VFD? Don't be shy. We had 3 guys last class that hadn't seen one yet. So I know we all, in different markets, we deal with different types of equipment. So if you get into a VFD, we've got 4 or 5 guys that are phenomenal at them. Like, give us a call. So by lowering the frequency on the VFD, it's going to slow down the compressor cycles. So therefore, it's going to lower the capacity. One thing I will tell you guys about VFDs on compressors. So the difference between VFDs on motors and VFDs on compressors have oil. So if you lower, with you using gravity flow type style pumps or slingers, centrifugal type pumps inside of your compressors, it's dangerous if you slow down your compressors too low. So anytime you're dealing with a VFD and a compressor, please check your specifications on speeds and time frames for speeds so that you don't run the compressor dry and end up having to change it. These compressors are extremely expensive to replace, and the reason why they're set to where they are is because that's where the manufacturer has them spec. Do not go outside of those specs to slow it down or ramp it up. If you're still having a capacity issue and you're slowing it way down, then we need to look at other options or other applications. So variable frequency motor, remember we have to have a specific motor for that. We just can't hook that up to anything. Up to 60% capacity reduction used on heat pumps and above 18 SEER. So we have seen a ton of VFD semi-hermetic reciprocating compressors showing up in a lot of our supermarket new applications. So if you guys see a Bitzer on a newer Costco rack, you'll see a big silver box in front of that Bitzer. That is a variable frequency drive reciprocating compressor. So if you have any questions on those, please let me know. So that's the end of this. We'll just run through the review questions really quick. Does anybody have any questions on anything we've just covered? Capacity controls, best practices, troubleshooting. Okay. I'm assuming you guys are experts then.
Can you repeat the whole class again, Jim?
The big thing about the big thing, guys, I want you to do is, like, if you can gather just today the importance of compression ratios, and then just kind of get a general idea of when you're dealing with a capacity control. Like, now that we know if we have a capacity control in play, let's look at the compression ratio, because that's what it's trying to control. If that's all you get from my class today, then it's a success to me. So if you see some kind of capacity control, whether it be a desuperheating valve or demand cooling or whatever, then let's set it up for the compression ratio. So the things that the touch points I really want you guys to understand today is compression ratios need to be anywhere from 1 to 3 to 1 to 6. That's our sweet spot. So we don't want to run higher than a 250-degree discharge, and you take that with your clamp 6 inches up the discharge line. So if you're running hotter than that, then we need to try to understand why we're not getting enough heat exchange properties in our compression cycle. So during that heated compression, we want to make sure we're still having good absorption with the refrigerant there. So we need to figure out why. We may need to add a liquid injection valve, or we may need to add a desuperheating valve. We may need to, and Copeland makes those Y valves you can strap to the discharge line that will inject refrigerant that we can tie into the liquid line. That will set you apart as a better technician. If you look at an application and you know that your superheat's dialed in, you know that your case is doing everything it can, but it may have been undersized in the piping, it may have had some issues, and the customer doesn't want you to run 200 more feet of pipe to reduce that compression ratio, then let's try and put a liquid injection valve on it. That's a lot cheaper repair, and you may be able to make it get by. So the big touch points, like I said today, are there's a lot that we covered and a lot of different types of capacities. Is check that compression ratio, know when you're dealing with a capacity control, know where to set, like know when you're dealing with unloaders, and know if your unloader's doing its job. If it's de-energized, is it loaded or unloaded? It's loaded. If it's energized, it's unloaded. So if you got, hopefully you guys are writing that down. Just write those couple things down. If that's all you got for my class today, great. You can go back to online and review my class, and then you can go get a little bit more every time that you watch it. But that's the big touch points I want you to get today. Is like, let's start looking at our compression ratios on self-contained ice machines, parallel rack systems, whatever. Let's start looking at our discharge temperatures, because that's going to cause black oil breakdown. So when you guys are dealing in Costco's and stuff, oil can be your worst enemy. So if you start getting breakdown conditions on any one of those 13 compressors tied to that rack, you guys are going to have a bad day. So we want to be doing those check downs, making sure that we're getting good cooling to those compressors, good cooling to that oil. So did that help, Sal, at all? Or we can redo it again?
Yeah, no, we're good.
Okay. All right, cool. Okay, guys, that's it for me today. If you guys have any other questions, please hit me up off-site, or any specifics. You know, we do this because we care and we want to help you. So appreciate you guys taking the time this morning, and let me know if you need anything from me.
Sounds good. Thank you.
Thanks, guys. Take care.
Desastre,